So you have question 13. It says, which is true about radioactive decay? 1, that the rate itself is exponential. That is true. There's the equation for rate. In radioactivity through individual nuclei, the decay cannot be predicted because it's random and it's unaffected by temperature and pressure. But for multiple nuclei, we can get a sense of the rate based on the decay constant. By looking at any one nucleus, we can't know for sure when it's going to decay. So all 3 statements are correct. D. So things that we know from 14 are that the count of x is half that of y. It says number of particles of x is half that of y. And the half-life of x is double that of y. And once the ratio of the activity in x to the activity of y, so it would be a of x over a of y. Well, we know that a is lambda n. And so we can solve for the x values in terms of the y values. We know that nx is 1/2 ny. And if the half-life is natural log of 2 over lambda, then lambda is natural log of 2 over the half-life. So the lambda of x is natural log of 2 over 2 times the half-life of y. And so I did that over here on the right with a of x and a of y. And so I can divvy them up and we can start isolating. And if we eliminate natural log of 2, the count of y, the half-life of y, we get 1/4 over 1, which is 1/4. And so the activity of x over the activity of y should be 1/4, a, which matches up with the mark scheme, which is strangely over here. All right. So looking at number 15, we have oxygen decaying into nitrogen with the emission of a beta particle. Does it say positron? Yeah, positron. That's why the beta particle has a charge of +1, not -1, and a gamma ray. So just by the kind of stoichiometry of it, I have 8, a proton count of 8 becoming a proton count of 7, so I have to emit another positive particle. That explains the beta particle. I'm also going from oxygen 14 to nitrogen 14, so it's the same nucleon count, and so I'm not emitting like an alpha particle, say. I need to emit a lepton, I guess, a positron, that has no nucleon count to it. And so that explains that right there, that piece right there. But so in the process of going from oxygen having a energy of 4.1 megaelectron volts to nitrogen having an energy of 2.3 electron volts, that right there, that's the beta particle. So the beta, so that positron, that beta positive particle is 1.8 megaelectron volts, so the answer is either A or B. Now let's talk about the gamma ray. Now the answer choices say the gamma ray is either 2.3 megaelectron volts or 4.1 megaelectron volts. Well, it can't be 4.1 megaelectron volts because that's from 4.1, the oxygen, all the way down to the ground state. I already have a particle, I already have a beta particle of 1.8 megaelectron volts. And so that's for the transition from oxygen to nitrogen. And so the rest of the energy would be the remaining from the excited state down to the ground state. And that's actually what happens with gamma rays. Gamma rays is actually the gamma ray emission. In the gamma emission, it's energy only, and that's for the excited state of the nucleus to the ground state of the nucleus. And so that nitrogen doesn't change. It's still nitrogen 14 with a proton count of 7, making it nitrogen. And it already spit out the beta particle to get from oxygen to nitrogen. So if it spits out some gamma ray energy, it's going from the excited state to the ground state. That's 2.3 megaelectron volts, and that gets us A, and the mark scheme agrees. All right, number 16 shows 2 graphs, one of activity and one of actual number of remaining nuclei. Activity is in becquerels, or decays per second. And it says, what's the decay constant of the nuclide? So one thing you can do is take a look at the graph for number of remaining nuclei, and remember that the half-life is the natural log of 2 over the decay constant. Therefore, the decay constant is the natural log of 2 over the half-life. Well, how can we get the half-life? We'll take a look at the graph of remaining nuclei, and at time 0, we have 1 times 10 to the 6 nuclei, and then basically half of that, 0.5 times 10 to the 6, occurs right here, which is at 1 second. So what that tells me is that the half-life for this nuclide is 1 second. And so lambda, the decay constant, therefore, is the natural log of 2 over 1, or just simply the natural log of 2, which is 0.7 seconds to the negative 1, which are the units for the decay constant, which agrees with the mark scheme, which is actually all the way over here because reasons. All right, number 17. So number 17, we saw a similar question. I forget what number it was. I think it was kind of like, the question was like, the fact that, it said, what explains the fact that beta particles have a continuous spectrum of energy, and like what accounts for that? And the answer was the existence of neutrinos. Oop, boop, was the bell. Was the existence of neutrinos. So this is literally the flip of the same question. It's like, why is there the existence of neutrinos? Because the energy of emitted beta particles has a continuous spectrum. So the answer is D, but it doesn't really explain the connection or why it's true. So I'll just go over that again a second time. So yeah, if the betas that pop out in beta emission are, if all energies of beta are possible, so you have a continuous spectrum of energy, then in order to maintain the total energy in the process, neutrinos are emitted as well. So if a high energy beta pops out, then a neutrino pops out, but it's low energy. If it's a low energy beta that pops out, then a high energy neutrino joins it, so that the sum of the energy is the same as the sum of the energy to start. But there you go. It's that beta situation. All right, choice D. Next question, 18. So for 18, we know that activity is lambda n, or lambda n naught e to the negative lambda t. Now you were thinking, it says after 3 half-lives, you would be using the A's lambda n naught e to the negative lambda t, but there's talking about 3 half-lives specifically. So you know that after each half-life, the count is half of what it was before. So at time 0, we have the starting count, the n naught. But after 1 half-life, it's half of that. 2 half-lives, it's a half of that, so a quarter. 3 half-lives is a half of that, an eighth. So after 3 half-lives, the count is an eighth of what we started with. Now we can see that the activity is the decay constant times n. And so the A naught, the original activity rate, is lambda times the original count. But after 3 half-lives, it's going to be 1/8 of what it was originally, because the count is now 1/8 of what we started with. But they're not asking about the original sample of n naught. They're talking about the second sample, which has 2 n naught. So then after 1 half-life, half of 2 is 1. After 2 half-lives, half of 1 is a half. And after 3 half-lives, half of a half is a quarter. So for that sample that started off with twice as many atoms, the count and the activity rate are a quarter of what they started with. This is what it says right here. So after 3 half-lives, A is A naught over 4, and that's going to be B, and that is what the mark scheme says, although the mark scheme is over here because reasons. That's 18. All right, let's look at 19. So for 19, it says that you have a pure sample of radioactive nuclide with n naught atoms at the starting time. After some time t has passed, there are n atoms left. The half-life is t 1/2. What's the decay rate proportional to? So we know that decay rate is lambda n, or lambda n naught e to the negative lambda t. But just looking at the expression, I can see that A is the decay constant times the remaining number of nucleons, the n count. And it's like, well, the decay constant, it's a constant, and I can show that with the half-life. The half-life itself is constant. I'm not sure all the work I did is really even necessary. You can just answer this question based on A is lambda n, and lambda is a constant, so A is directly proportional to the number of remaining nuclei. So that would be n, and so 19 is choice A. This one is special. They seem to break the page in between the choices, so the rest of the question is here. Becquerels, so C is 7100, D is 75. Let's go fix that. There we go, there's the whole question. Okay, so for number 20, things we know the half-life is 8 seconds. We know the original activity is 10,000 becquerels, and wants to know the activity up to 4 seconds. Well, the half-life is 8 seconds, so 4 seconds is half of the half-life, but it doesn't really work that way. You can double the half-life to get a quarter of the activity or of the sample, but 4 seconds going back up the curve doesn't really work that way. So I think we're finally going to use A equals lambda n naught e to the negative lambda t. So things that we know, first of all, we can also take that expression that if A is lambda n, then A naught is lambda m naught. So in that expression, A equals lambda n naught e to the negative lambda t, we can sub in A naught, the original activity, for lambda n naught. So that's where this is coming from. That's where that expression is coming from. I know my original activity is 10,000 becquerels, so really I just have to put in e to the negative lambda t. So I know that the half-life is natural log of 2 over lambda, so lambda is natural log of 2 over the half-life. The half-life is 8 seconds, and t is going to be 4 seconds. And so I substitute in the 10,000 becquerels right here, and I put in the time and the half-life, and that resolves to 10,000 times e to the negative natural log of 2 over 2. There's a expression in physics where we say we leave it as a exercise to the reader to resolve. Actually, no, I won't. I'm going to show you how we get from e to the negative natural log 2 over 2 to 1 over radical 2. But anyway, 1 over radical 2 times 10,000 is 7,100, and so it's choice C, which agrees with the mark scheme, which is over here, of course, because they're annoying. But let me just show you how we get from e to the negative natural log of 2 over 2 to 1 over radical 2. So e to the negative natural log of 2 over 2, e to the negative anything, or anything raised to the negative power, is 1 over, is reciprocal. So we have 1 over e to the positive natural log of 2 over 2. Now, even that's a quotient. Natural log of 2 over 2 is a quotient, not a product, but regardless, quotient or product, a raised to the nm is equal to a raised to the n raised to the m. So I basically broke apart e to the natural log of 2, and I raised that to the 1/2. Now, what does that do for me? E to the natural log of anything is that thing. So therefore, this expression resolves e to the natural log of 2 simply becomes 2. And it'd be 2 to the 1/2. Anything to the 1/2, of course, is radical. So e to the natural log of 2 over 2 becomes 1 over radical 2. The interesting thing is that this also equals sine of 45. So there's a connection here between natural logs and trigonometry. I'll leave that as an exercise for the reader to connect those dots. But that sine of 45 is not relevant, but that is how I got from e to the natural log of 2 over 2 to 1 over radical 2. But anyway, 7,100 becquerels, choice C. Next question. I'm pushing up on 15 minutes anyway. 2 more questions, we can knock these out. 21. So with 21, here's another one. Evidence things. We had 2 questions about beta decay and neutrinos, but this is gamma decay. The deal with gamma decay The thing about gamma rays is that they're energy only. They have no mass at all, no charge at all. So it's not going to change the nature of the nucleus. It's not losing any nucleons. It's not switching any protons. It's not creating any particles. We don't need to create any antimatter. It's just emitting energy. But if it's not changing the nucleus, then what's happening? I mean, the nucleus is losing energy, so how is it losing energy without losing mass? It doesn't lose mass, it just loses energy. But where does the energy come from? It comes from the fact that the nucleus was originally excited, and now it is simply not excited. It's to the ground state within the nucleus itself. So we're dealing with energy levels here, but energy levels within the nucleus. And so that is B. Now you might remember that the nucleus, all nuclei have the same density, which are just pretty much nuclei packed as tight as possible with no space in between. So if they're packed as tight as possible, how could they be falling from one energy level to another? That has to do with quantum mechanics, the fact that they're all actually wave functions interacting with each other. And so, like, the notion of empty space is funky when you start getting into quantum physics. Fun. We're not going to go there. Trust me, it's choice B. Number 22. And here's 22. It says positions, I need my glasses, not positrons, positions of stable nuclei are plotted by neutron number n and proton number p. Graph indicates a dotted line for which n equals p, which graph shows the line of stable nuclides and a shaded region where unstable nuclei emit beta minus particles. All right, let's look at the graphs. Well, if you remember the graphs, eventually, like for low atomic numbers, n does approximately equal p, but then as you go higher in nucleon number, I suppose, you're going to need more neutrons than protons, and so it does begin to curve that as the proton count increases, the neutron count increases more than the protons do. So it's not A and it's not B, because that shows more protons than neutrons, which is not true. If that were true, you would have too much electrostatic force, and the nucleus would blow apart. So we actually need neutral neutrons and the gluons they bring to hold the nucleus together to counteract that electrostatic force. But let's take a look at the two graphs. So the n equals p is dashed for a reason, because that's not what actually happens. The solid line is what actually happens. But look at the shaded area. We have shaded area to the right, towards the dashed line, or shaded area to the left, away from the dashed line. Well, which is it? I mean, yeah, Mark's scheme says it's D, but why is it D? Okay, so I'm going to use D as my answer, as my example, because it's the answer, but I'm going to show you why. First, it's important that it's emitting beta minus particles. They mentioned that. If it was beta plus, this would be C if it was beta plus. Now, why is that? So the line itself, not the dashed line, but this line right here, I'm making that a little bit darker. That line right there, that's the line of stable nuclides. So those nuclides are stable and they're not going to decay. So you have decay actually on both sides of that line. All right, so to the left of the line we have beta minus decay. To the right of the line we have beta plus decay. Now, why? Like, what's the goal? What are they trying to get to? They're trying to get to the stable line. So the nuclides on the left, they have more neutrons than protons, and so the area that is stable is actually, like, if I'm on the left, in order to become stable, I actually have to move to the right. I need to get closer to that black line. I need to increase my proton count or increase my positive count. So those guys need to be more positive in order to be stable. So to become more positive, they're going to spit out negatives. So those guys will emit beta minus, so the answer is D, because they were talking about beta minus. On the right side, they need to be more negative. They need to move to the left to get to the black line. So they need to be less positive and more negative. So if it's to the right of the curve, they're going to emit positive particles to become less positive and move to the left to be closer to that curve. So yes, since I'm emitting beta minus, the shaded area is going to be to the left of the stability curve, and my mark scheme is D. And that's the last one. So thank you very much.